Hey guys, welcome back. I hope you enjoyed your fall break. So today I'm giving you guys a practice quiz for regression. So we'll be taking the test for bivariate data in about 2 weeks. So anyway, we'll take a quiz here and I'll give you guys really good feedback on the quiz as well. So let's go ahead and get right into this. You can watch the solutions to the practice quiz as soon as you've actually taken the practice quiz itself. Okay, so if you just watch the solutions, it won't help you. So the whole point is you need to try it out yourself, see what you do know, and then watch it with me to see if you did as well as you thought you did. All right, so on number one, it says a silly psychologist student gathers data on the shoe size of his 30 classmates and their GPAs. The correlation coefficient between these two variables is most likely to be what? So it is rather silly. We wouldn't expect shoe size and GPAs to be associated with each other at all. So we know at the very least the strongest negative one, like a perfect correlation, would be -1, and the most it could be is +1. But we're expecting something in the middle, something close to 0. It might be slightly negative, might be slightly positive, but regardless, we would say there was no association, or there would not be any evidence of association. So it would be something near 0, which would be C as in Charlie. All right, number two, the Lakeside restaurant found the correlation between daily temperature and the number of meals they served to be 0.4. On a day when the temperature was 2 standard deviations above the mean, the number of meals they should plan on serving would have a z-score of what? So this is going to be basically regression to the mean. So if our explanatory variable is 2 standard deviations above the mean, then using the correlation coefficient, that's kind of like our scale factor that would allow us to tell us the strength of the amount of confidence that we would have to deviate along with the explanatory variable for our response variable. So what we do is the predicted response variable z-score is going to be equal to the correlation coefficient times the explanatory z-score, and so that would be 0.4 times 2, a +2 because it was 2 standard deviations above the mean. So that would allow us to go out to about 0.8, a +0.8. Which would be here. So the fact that our predictions are always closer to the mean than the explanatory is because we always regress back to the mean. We always back our confidence off of what our explanatory variable is because of the correlation coefficient is always going to be less than 1. So the best that it could be, if it was a correlation of 1, then we could say that they were the same, but it'll always be something less than that because we never have like a perfect correlation. For families who live in apartments, the correlation between family income and the amount of rent they pay is 0.6. So, which is true. So in general, families with higher income pay more rent. So as long as it's not implying a causal relationship, we'd be fine, because remember, correlation is not causation. So we don't know if it's that they pay more in rent because they have more income, or because they have more income they find apartments with more rent. You know, we can't really tell what direction it goes in. So as long as it's just a general association, in general families with higher incomes pay more in rent, or they tend to pay more in rent, that would be true. So there's no problems with that part here. On average, families spend 60%. Okay, so the correlation is 0.6. That's not 60% of their income on rent. That's not what they're talking about anyway. So that one would not be true. That's gonna be false. The regression line passes through 60% of the income rent data points. So that's not what the 60% is either. So the correlation coefficient is going to tell us the slope of the regression model. It also gives us kind of our model for how we would run our regression to the mean. So this is not going to be true either. So the only one that's true is going to be A as an alpha. Number 4, regression analysis of statistics students' test scores and the number of hours they spent studying on work found that R squared, which is the correlation of determination, coefficient of determination of 0.32. Which of these is true? So 32% of student test scores can be correctly predicted with the model. No, in fact, it really is how far off it is from the prediction. It's kind of what we're measuring, but we don't expect to ever be exactly right on with the model. We just want the model to be close to the true values. So that's not actually what we're looking for here. It would be nice, but that's not how we interpret the coefficient of determination. Homework accounts for 32% of your grade. No, that's not true. And that's not a correct interpretation of the R square. The correlation of the correlation squared, which is the coefficient of determination, is actually this. 32% of the variation in students' test scores can be accounted for by the model. What that tells us is that we can remove 32% of the variation by using this model instead of just guessing the mean test scores across the board. So anyway, 32% chance you'll get the score the model predicts for you. Again, that's not how this works. So none of these are good interpretations of the R squared. The R squared is going to be the amount of variation that can be removed by using the model from the response variable. All right, number 5, variables x and y have a correlation of 0.4. If we decrease the value of x, so if we shift everything by 0.1, how is that going to change the correlation? Well, if you remember, the correlation is calculated by the sum of the products of the z-scores. So whenever we shift things, it's not going to actually change their z-scores, so where they are in the whole distribution. Like if it's still above the mean, it's still going to be above the mean, right? So that's not going to change the correlation. And then if we double each value, so when we double just like we showed here, we're shifting here or scaling, that's sorry, that is going to double the standard deviation or whatever our that would double the standard deviation. But when we do a z-score, we're actually going to end up dividing it by the standard deviation anyway. So it doesn't matter if our distributions are really spread out or if they're really consistent, because we're dividing by the standard deviations for that individual variable. So that wouldn't actually change the z-scores. And then interchange them. So if we switch it from x and y, well, what happens because of the commutative property multiplication? If I switch the order of the z-score of x and the z-score of y, it doesn't matter. Just like as 2 times 3 is the same thing as 3 times 2, it doesn't matter if you switch the order. So what's interesting is if we shift the values by 0.1, if we double the values by scaling, and then we switch the x and the y, the new correlation is still exactly the same. So it's still going to be 0.4. So what you need to learn from that essentially is that the correlation is pretty impervious to shifting, scaling, or even switching the x and the y terms. Kind of cool. All right, number 6, the residual plot for a linear model is shown. So the residuals is graphing how far off these points are from the actual model. So this line here is what we were predicting. Positive residuals means the actual was more than expected. Negatives 1 would mean that they were less than expected. What we're looking for is for no pattern at all. And this one shows a clear curve pattern. So if we actually had the original scatter plot, the scatter plot for this one might look something, well, isn't that lovely? Might look something along the lines of that. And so if I graphed out a line and try to fit that linear model, what you'll notice is that you have points on the top and then they're below and then they go back up to the top again. If I actually drew that out right, yeah, so something like that. And that's why we have here these points that are positive, more than expected, less than expected, and then back to positive again. So the curvature shows up pretty easily when you look at the residual plot, and that's why we always graph it out. And we're looking for something with no pattern, so just as many points below it that would be above it, then that would make it okay. Okay, so the linear model is okay because it's approximately the same number of points above and below it. No, that's pretty much always going to happen. So, or at least their averages are going to average out to 0. The linear model, sorry, the sum of the residuals will always be equal to 0, which is kind of interesting. The linear model is okay because the association between the two variables is fairly strong. No, it's actually better if we re-express it when it's curved, even if it is pretty strong, because then it'll be even stronger. So that's not true. The linear model is no good because the correlation is near 0. Not necessarily true. Yeah, the correlation of the residual plot would be near 0, but that's not what we're looking at here. The linear model, because yeah, by the way, this would be the scatter plot, which is graphing the x by the y, and then over here we have the residual plot, which graphs the difference between the actual minus the predicted, which is the y hat, and then usually along the x-axis here. Sometimes this is actually the y hat, the predicted down here, but we usually don't work with those. I prefer to read it about the x-axis. All right, linear model is no good because some residuals are large. Okay, well, as long as we don't have any like outliers that are like far way up by themselves, so if all the data was consistent, but there was one by itself, then we'd have an issue, but that's not the case here. There's plenty of them all by each other. Linear model is no good because there's a curve in the residuals. Yeah, that's the problem we have, is because we have curvature in the residuals. All right, number 7, all the following statements except one contains a mistake. Which of the following statements could be true? So for sample packages, correlation between weight and shipping time is 1 point. Okay, well, you can't have a correlation stronger than 1, right? So that's not right. Correlation between the length of a tail, and the breed of the cats is 0.17. Okay, so this is okay because it's less than 1 of a magnitude, but the problem is the breed of cats here. So we can't really do a scatter plot for categorical data. Breed of cat would be broken down into categories, right? So that's not appropriate at all. You can't do a scatter plot with that, because how would you put, what would you put on the, is that a Maine Coon, and over here you have a Siamese cat, and then I really don't know any other breeds of cats. Kind of embarrassing. A tabby cat? I don't know. I have no idea. Breeds of dogs, I think, are more prevalent. All right, a new car owner keeps track of his average fuel economy for each tank and how many miles he was able to drive until the fuel light comes on. So basically the range. The correlation between the fuel economy and the range is there. All right, so fuel economy and miles per gallon range, yeah, and those are going to be pretty high correlation. So that one's actually just fine because you're dealing quantitative data, and it's not more than 1. The problem here, correlation between fuel economy and range, so the problem is that you don't have units, because correlation is calculated from z-scores, and z-scores get rid of the units by dividing by the standard deviation, which is in terms of their units. So they're unitless. And that's what allows us to compare a z-score from apples to a z-score of oranges. So like long jump compared to shot put. So that's the whole point of them, is that they don't have units, which is what's really nice about them. So anyway, if you put units with the correlation, then it's not correct, because correlation does not have units. All right, the R-squared, the coefficient of determination for the fuel economy and range. Okay, well, we can't have more than 1. So whenever we square 1, it's not going to be more than 100%, right? Can we remove more than 100% of the variation? No, that's not possible, right? So at most, this could never be is 100%. So that's not going to be true either. Okay, so anyway, good stuff.